Hello, listener. Welcome back to the iScientist podcast. This is episode 2, as always, or as for the second time. I'm your host, Jonah Walker, and we are here with a distinguished guest. Real great guy. You know, one of my closest friends of all time, and might I just say, one of the smartest engineers in the smartest program at McMaster.
I wouldn't say that that's true.
I would say that that's true. Ladies and gentlemen, please welcome Josh Campbell to the podcast.
Thank you. I really appreciate being here. This is a very cool space, a cool idea.
Thank you.
Kudos to you for kicking this all off. This seems like a very cool space for everyone to sort of just talk about their little domain. Because I feel like even you'll have a lot of people that come through that you're friends with or that you know in your program, but and they could have so much experience, but you never really get to hear a lot of the side of that. And I think people have some really valuable stuff to say from the experience that they've gained.
Exactly. I think the best science conversations I've had has just been people freestyling in the library on their research, right? And from my perspective, oh yeah, by the way, I should have mentioned this in the intro. I am also senior editor of the iScientist undergraduate journal, which is the affiliated journal of this podcast.
Nice.
Description. Find the link to check out the journal in the description. Also, shout out to Lions New Media Center for letting us use their podcast studio.
Thank you, Lions New Media Center. It's lovely. We got snacks and everything when we walked in.
I know, we got snacks.
They're so sweet.
So Josh is here today to talk to us about his experience at, I don't know, would you call it an engineering firm?
Yeah, I don't know. It's given that it's a startup, it's kind of tough to pinpoint it on just one thing. But yeah, we could say engineering firm.
Yeah, definitely. So if we call it, the engineering firm is called Noze. And for the first question, I was hoping you could just walk us through the about us page of their website. You know, give us the high level, what is Noze, what do you guys do?
Yeah, for sure. And for the audio listener, I do have my laptop up, but I promise I'm not just looking at it and just reading off the website. So Noze started many years ago. They had this whole idea of digitizing all of the senses. So we know tactile senses have some digitization already. Obviously sight, we have photos everywhere, smells-ish, but that was kind of the one that was lacking, was smell. And there was a big market for it and kind of a market gap, to be frank. A lot of people had come up with the ideas, or a few people had come up with the ideas of digitizing scent and sort of collecting that data that's stored just in the air we breathe and all of that and converting it to something a lot more useful. But they sort of took an interesting approach. So they bought a patent off of actually NASA's JPL program, so the Jet Propulsion Laboratory. So back then, what they were doing is they were using this technology to send up to the space station. And what they were using it for was air quality monitoring and control. So they wanted to know, if something was going wrong or, levels were dropping or anything, how quickly could they detect it? If a smell was in the air, could they pinpoint where it was coming from and sort of figure out if there were failures alongside that? And it was pretty cool. So Noze took this idea, took this technology that JPL ended up kind of archiving for a little bit, and it got new life. And so what Noze started to do was kind of go back into that domain of air quality, but with new technology that had been there since JPL kind of left the program, and they ended up reinforcing it with this beautifully complex AI algorithm that was able to act as more of a predictive model and show based on what's happening what could happen, and it took a lot of moving parts and a lot of people, but what they ended up doing was creating an air quality control monitor. So it was actually available through their website. The CTO, he was an amazing person. He had this awesome story just about how they were like, well, we think that people might want this, but how do we know if they actually do? So essentially, they were just like, well, let's see what the people actually want. So they put it on their website as a phantom, like, you can buy these, and tried to see, like, if they make it, will they come type thing. And they sold out within, like, a few months, I think was the number. I could be wrong on that, but it was like incredibly quickly, and they were out. That was it. And so they realized, okay, like, clearly if we make it,
clearly there's a market for this.
Clearly there's a market for this, and their model was incredible. They took it to a bunch of like expos and everything. I'm high leveling this. I know I'm leaving out a lot of details in the steps.
We're gonna get back to those. Don't you worry.
We can get back to some of those. But they were doing a lot of like going to shows and showing people and being like, okay, can you, like, put, it was a sensor. It kind of looked like this microphone, honestly, like, but it was red. And what they said is, like, each person could come by and you would put something underneath it. And within a couple seconds, the machine would read it and tell you exactly what's in the air.
Right.
And they saw that and they were like, well, this is awesome because you can use this as an air quality control monitor. You can also use it in farming. You could throw it in the corner of a warehouse or whatever, and you can figure out when your crops are going bad. You could throw it, in households as a carbon monoxide detector. What they did, and where they really saw a ton of business, was when they actually looked to put it in homes during COVID. Okay. So they could do an analysis of the air, and it would show you. It would, like, see, well, like, how safe is the air that I'm like actually.
It could detect COVID in the air.
I don't want to be like 100% on that, but from what I understood, it could give you if there was higher risk.
Okay.
Not necessarily like, is there COVID in this room right now?
True.
But, like, are your risks elevated based on what it's capturing?
Facts.
So yeah, that's kind of I mean, that was where they stopped, and then as this technology got really great, they said, well, we can make an impact with this. We can. Our model is solid. It can predict stuff, like how long it would take to cook chicken. And stuff like that. Like, is your chicken done based on it just, like, sitting in the corner and absorbing all these VOCs, which I'm going to say VOCs a lot. For those of you who don't know, a VOC is a volatile organic compound. So it's something that is, just part of the air that you breathe. It's all around. There are organics that you can sample.
Can you give us a couple examples of what a VOC is?
Yeah. So, like, some big ones, like acetone, isoprene, butanol, all those are sort of some big ones off the top of my head that I think we're a lot of focused on. But obviously there's, like, a ton within the air. Like, our air is composed of, mostly nitrogen. We got some oxygen, a bunch of other stuff. And it's part of that small percentage at the bottom that you can actually, you can make use of that. So they saw that there was a huge potential for this technology, because it wasn't only able to do some of this, like, small level stuff, but it had the potential to do something huge, something really impactful. And not that it wasn't impactful before, but definitely a lot more. So they pivoted to healthcare. And
when did they pivot to healthcare around?
Oh, that would have been, I want to say 2020, like before the pandemic. Okay. Or right during the pandemic, actually, they decided to make a switch. Because when I joined up, they were still developing everything. It wasn't like they had their product and I was just kind of working on the side. Like, we were truly in a huge R&D movement and push. And so what they saw with their technology is that, just as a dog can sense if somebody has high blood pressure or is their insulin levels too high or too low, they thought, well, why couldn't this technology do something similar? If a dog can do it, then
come on,
it must be easy. But yeah, so they sort of applied that into healthcare, and then they took some big diseases and they wanted to kind of be able to diagnose, to be a supplement, to be another tool in the toolbox to say, do I not have that?
Right.
So
it's now working to diagnose some major illnesses. Which illnesses?
Yeah. I mean, I'm going to be completely frank with you. I am still under my NDA, so I don't know a ton that I could talk about. That's not public domain. But from what I know is public domain, is that we are looking. They were not us. I'm no longer affiliated. But they were looking at breast cancer screening.
Wow.
Tuberculosis and high blood pressure.
Can you tell me what is not public domain and I just bleep it out?
Yeah.
Can you do it right now?
No.
Bleep it out. I'll bleep it out. I swear to God.
No.
Okay. I'm going to cut that part out.
That's the point of an NDA. Anyway, so yeah, that was sort of the shift there, the idea, that seed, and Ashok Malasamani, who's the CTO, he really had this push because everyone's affected by some of those big illnesses, especially when you're looking at the cancers. I don't know. I know I have it in a lot of my family, and I know that there's a lot of families that are kind of similar that also are in that situation where they've been affected by it. And if you can have another method of diagnosing, or maybe even just something that beats the current gold standard,
right,
you're in business.
That's what you want.
And yeah, and obviously they're not in it to make a ton of money. They're in it to.
They're healthcare. It's a healthcare business.
It's a healthcare business.
From what I'm gathering, they went from an air purification and
not purification, just monitoring.
Air monitoring company to a healthcare company.
Yep.
That is really fascinating. So I just want to take a quick step back here, and I want you to just talk a little bit about the timeline that you were at Noze, right, and the role that you had there.
For sure. I came into Noze January 2024. I was there for 8 months, so just until the end of August 2024. And it was a really interesting time that I was there. I think one of my most notable experiences right at the start was figuring out that like the building was brand new that we went to. Like we moved buildings in January. And so I remember showing up and I was like, oh my goodness, this office is like dead. There's like no monitors, no pictures of anybody's family. I was like, oh man, this is gonna be a scary place to work. And then I met Erica Gundenson. I think that's her last name. Erica was lovely. She was part of the CEO's office, and she was so great during the transition period. But yeah, she like made it known. She was like, "This is a new office. I swear, we're gonna get this all kicked off soon." So yeah, like when I got there, our labs weren't even fully set up. But yeah, I quickly picked up. Everything was great. There was some like minor hiccups, but other than that, like we got up and running and I started with the product development team. So our work was mostly focused on the actual device itself.
Okay.
So at the time, we had a diagnostic breathalyzer, which we still have right now, where the whole goal of the breathalyzer is to have a patient breathe in 5 times, a little depending, but roughly 5 times. Their breath sample gets forced over the sensor chip, and all the VOCs from that person's breath are captured in there. So there's a ton of complex systems that are involved with that. So for instance, like they had their own sensor team. So there was a team just dedicated to the development of the sensor. And it's Dr. Jayan, he was the head of that team, and he did some incredible work just developing the sensor from not necessarily ground up. He was the first employee there. So he had been there since Noze day one, back when they were still, grabbing the patent from JPL and working from there. But so their team mostly focused on the sensor. There was also a team working sort of on the AI algorithm and the model. There were some back-end teams that were doing sort of, like the honestly, I'm going to butcher it because I don't really know. But it was above my pay grade.
It's not your team.
It wasn't my team, and it was above my pay grade. And they were fantastic at what they did.
Listener, that might be above our NDA as well.
That might be above our NDA. No, they were incredible. And then there was also a scent generation team. So it wasn't necessarily called that, but it went through a few name changes. But kind of like the best way I could describe it is they were trying to create data sets, essentially. So that was their role. And then there was our team, the product development team. And I like to think that we were the we were just the the guys who took the input and tried to make the device
True.
nice, but also like functionally a lot better. So yeah, it was an incredible time. I think everybody at Noze, this is going to be not the last time I say that, but incredible experience.
Fair enough. Okay, so right now for the audio listener, I'm gonna flash a. Can I put a picture of the device?
Yeah.
Okay.
Yeah, for sure.
Okay, I'm not actually gonna do it, but I'm just gonna edit it over.
Okay.
So right now we're looking. Well, actually, do you want to pull up a picture of the device? Because my next question is going to be, can you just describe what the device looks like for us?
Yeah, we can. So
okay.
We can look at this one. This is on the website, by the way, so I'm not violating anything. I promise.
Noze.ca/technology if you guys want to go check this out.
It's up there.
Okay.
Very cool website.
So run us through the design of this breathalyzer here.
Yeah, for sure. I mean, there's going to be not a lot I can say about like component level, but I can go through and talk about sort of like the process that we went around. So what you're looking at right here is the breathalyzer V0.5. So I was actually one of the first people to ever build one of these. It was me and one other person, and that was kind of our task. I did a lot of like mentoring under the initial like designers who were there. His name was Cam Viedev, and he's a brilliant mechatronics engineer. And he did a lot of the design work and the assembly work. Him, as well as Happy, Krish, those were the guys I worked with the most in my team. So what they were doing, what Cam sort of did was kept the internals of our device same, but we have this nice shiny shell, and it looks very lovely. And it is made.
It does look really good.
Yeah, it's heavy. It's made out of aluminum, but we had like we had.
It's made out of aluminum?
Our first version was, but we had some changes that we made to make it like a lighter version too, more portable. But yeah, I can kind of go through the design. So what we see right here is the mouthpiece and then the actual device itself. Okay. So the mouthpiece is pretty cool. It has more of a purpose than just a thing to breathe into, because you could breathe into a straw, a stick, whatever. There's a ton of other options, but what we really wanted to do with this was optimize the flow delivery. So that was like a big role of our team was, okay, this person has a sample. We need to get sample to chip in the most efficient, best way possible to get the most pure sample to read. So that's what our job was. So it all started with the mouthpiece. The mouthpiece of the design not only needed to be comfortable for somebody to breathe into, but it actually had to diverge the flow in a pattern that we liked. Okay. And obviously it's coming off of mostly a turbulent flow. So a lot of mixing, but mixing could have been good, could have been bad. There was a lot of moving parts where we were investigating a lot of these things.
Would you mind, in layman's terms, telling us what turbulent flow is?
Yeah, for sure. So turbulent flow is a flow that has a lot of fluctuations in it. Okay. So, I mean, turbulent flow through a pipe is mostly uniform, except due to the fluctuations, you have a lot of, it's a high velocity gradient near the wall. There's a lot of mixing. In layman's terms, a lot of mixing.
As opposed to...
Laminar flow.
Laminar flow. I knew that, listener.
Nice.
Yeah, and I'll flash a picture of laminar flow up for those who don't know. But that's just like, it's like those satisfying videos when you cut open a bag 100%. And it's just like a straight stream of water coming in. Okay.
Yeah, if you can hit it under a certain Reynolds number for a given thing, you can get nice, beautiful, pretty laminar flow. Okay. But for all intents and purposes, we wanted turbulent flow when I was there. So for a lot of the design, it was in the mouthpiece. It was around that, and then also making it look nice, because you can do both.
It does look very nice.
You can do both at the same time. This was a phenomenal design. So the next part that is actually really interesting, I kind of have to talk about a little bit of the breath sample itself. So the breath sample, when we are trying to diagnose a disease or trying to get a sample collection going, we care about a lot of things. We care about a lot of the profiles, how quickly we see some responses on the sensor, like the time. There's tons of markers that we look for. One thing in common, though, with all of these diagnostic breathalyzers or breath devices that we have seen, like all across the market, this is not just unique here, but is humidity. Humidity in your breath causes all sorts of issues.
Interesting.
Yeah.
Interesting.
So a sample having too much humidity messes with a million things. Well, when you think of a raw sensor, right, you're thinking of introducing hot, humid, high pressurized air into anything. It's a recipe for disaster, and it's not scalable, right? You have sensors that die out really quickly.
And when I'm thinking of the sensor, I'm thinking of a little green plate with like lots of little electronics on it. Am I wrong for thinking
No,
that?
you would be pretty close. I actually think they do have a photo.
We're in luck.
Yeah.
Whoa.
There we go. Yeah, so we can see the sensor chip. You can actually see it on screen. It is on their website as well. It's an incredible piece of technology, but just to get
that thing's dope.
Yeah, just to get kind of a visual of what your sensor looks like that's it.
Yeah, does not look like it would mix well with water.
No. Unsurprisingly, no. Actually, a funny story on one of my first days, I didn't really know like what the lab, because we didn't have lab protocol because we didn't really have a lab.
Right.
So there was like a fresh batch of sensors sitting out on the table in the lab, and I come in with my water bottle, plop my water bottle right down beside them, and I thought one of my coworkers was gonna have a heart attack. I was like, oh my god, I am so sorry. And like, needless to say, obviously water was banned in the labs after that, and I was like, my bad.
You only make that mistake once.
Truly,
only make
that
mistake once.
Only made it once. Left my water bottle at my desk at all times. Post that.
So how big is this device here? Like just like give me like a hand like.
Yeah, for sure. So the whole ergonomics was to be so that anybody could fit their hand over top of it. And then when you were breathing into it, it's not super heavy. So it's not weighing you down or anything. It's pretty standard. Like it would be honestly like if you're at a microphone and you just give a breath.
Right. Yeah. So for the audio listener, Josh here just made a circle with his hands, and I would describe it as probably the size of like a large restaurant hamburger is what he's put together here.
Yeah, that's a good visualization.
Like a large restaurant hamburger.
For sure.
Yeah, so
and then the rest of it, if you want me to go through like the rest of the sample then goes into sort of like a collection chamber. And this is where again we want some of that mixing, some of this, some of that. And then it gets forced over our sensor.
Sure.
So a lot of the internals, I mean, I can't go over a ton of it, but there's a lot of parts that are really interesting. Like, for instance, all of your breath isn't important to us. It really isn't. It's a lot of it's that tidal volume that you have here, but we actually want the alveolar breath. I don't know if you're too familiar with like the breath cycles.
No, like I totally am, but like for those of us who may not be, like maybe we should go over it.
So when you're breathing, just normally, it's called like your tidal volume. Okay. And for everybody, it's going to be a little bit different, but I'm going to butcher the amounts. I believe it's 500 milliliters. Okay. Could be wrong on that. And then you have your total inhalation volume, which is if you like take a big breath in, you're going to have a little bit. Okay. And then your total expiratory volume, which is like, you're really giving it. And then you have a low residual at the end, as you always should. And that makes up your total amount. And the alveolar portion of the breath is that small amount near the end of your expiratory breath. Right. So it's the last little that you're really giving out that we really care about that. That's where the most concentration of VOCs really is. Okay. Everything else is just kind of like, if your breath's moving up and down, it's mostly saying it's not necessarily going deep in your lungs. And what you really want to tap into when you're trying to sample breath is interaction with the bloodstream. Mm-hmm. So if you're getting out that air that's been trapped around your capillary beds for a long time in the alveoli and now has mixed and there's been tons of gas exchange, you want to get that out because once we get that out, that's where we can do something with that. Right. So it's really interesting because if you're breathing into this thing, it was a huge issue, and we came up with a mechanism to figure out we can now capture the sample. Everything else sucked. We didn't want that. Now we can start. Right. And so that was a really cool, a really cool design feature of all of it, which I thought was something I never considered before. Right. But then again, it's not like I had too much experience in breath capturing devices before I walked in there.
Not everyone's a breath capturing expert.
No,
like I am.
Yeah, honestly, you strike me as one. Just a little hobby.
So, okay, I have a question.
For sure.
Do you want more turbulent flow in your mouthpiece because that increases the exposure of your chip to the VOCs?
And this is where I'm going to get trapped by my NDA. So there was a lot of research behind it.
Okay.
And a lot of in-house testing. And the conclusions that we drew were sometimes a little bit on either side.
Right.
But at the end of the day, I think it's, in my opinion, what makes the most sense is more mixing.
Right.
More mixing of air. If you can't separate everything out layer by layer, or if you are separating everything out layer by layer, how do you know you're not missing anything?
Sure.
And to separate everything into nice laminar flow every single time for every single patient becomes difficult. So instead, make everything chaos, make everything messy, make everything weird. And if you can sample weird, messy, and chaotic, you can do it anywhere. So looking for those pristine conditions all the time isn't feasible. It's not a way to do all this, and it's not scalable. It's not a method to be able to have one breathalyzer be able to diagnose you and the people outside and the people staying there from a different breathalyzer that's diagnosing everybody on the second floor, but
Sure.
that they are diagnosing the same thing. And that's another really cool part of the technology that I think I failed to mention was the best part about it was how scalable it was. That chip can be manufactured a lot. And the way that the AI algorithm worked was that it wasn't chip specific. So one chip capturing samples on one device didn't build the algorithm and then all of them try to do, because each chip is going to be a little bit different. That's the reality of manufacturing. Right. And if you want to have a scalable business, you need to solve that problem. And they did a phenomenal job of solving that problem. It wasn't that, I used one device this day and I got this result, and I used another device 3 days later and got a different result. Like, I was nailing the same metrics again and again and again. And that's just sort of a testament to how much work goes into sort of having that foresight, even as a startup, on like how do we be big? How do we be a big company that can do a lot with the small manpower? And how do you think ahead just like that? And I think it is truly a testament to that foresight that a lot of the top people at the company really had.
Sure. So my next question for you, I am 90% sure this is going to violate your NDA. But I want to ask, because I'm curious. This is a podcast for mostly iSize that we're going to be listening to this, and all of us are really beholden to scientific publishing.
Oh,
and
for sure.
And you have to prove outcomes to a certain statistic, right?
Yep.
So I want to ask, do you think there's a difference between like corporate R&D versus scientific publishing in terms of what sort of statistic and what sort of level you need to prove your results to?
It's difficult. I would say, and I actually don't think this violates anything. I think it's a nice win. But I think it's really case specific potentially. But from my experience, what they were going for, and you've seen this with a lot of other businesses in biotech. I can touch on those later, but when you look at a company like this, they only succeed if they're better than what already exists.
Right.
So really, when you're looking at it, like if you're publishing a scientific paper, it is a lot of for just let's this discovery. Let's put this publication out to the world. We're testing it against some null hypothesis as a p-value of whatever. We want to see statistical significance between what we do and what we think. Testing our hypothesis. The hypothesis of this company is really more about, are we better than what's out there? Are we on par with what's out there? Can we be better than what's out there? Because if you're not hitting that, you don't have a business, right? And so at the end of the day, they're what they're trying to get at, and in all the R&D that we were doing, was essentially how can we optimize this to be better than a mammogram?
Yeah.
Because if that's what the gold standard is right now, which honestly is not the best. For younger women and with low breast tissue density, it's like quite poor. It can be like under 50% accurate. And that's
not ideal.
No. And if you can be better than that in some regard, and it's not just with breast cancer, because obviously this was not, the idea was not to make a one-stop shop device, but to make one that can do a lot. you need to be better than the gold standard. So whatever field you would be looking at, you can just look for what's the best thing out there. Mm-hmm. That's what we're comparing to. Yeah. And you can see like firms that do R&D that don't try to go to the gold standard or like try to fake it till they make it or fake results. Like they don't do well. I forget what her name was, but that
Theranos?
Yeah. Theranos. Like it was they just faked it. Mm-hmm. And they weren't at the gold standard. They weren't even close to the gold standard. But you can see how you can build up all this hype, but that hype needs foundation.
Right.
And that foundation comes from your tech.
Sure.
And I mean, I feel like I'm just going to be the poster boy for this company, but they have the tech. The tech is there. So now it's just about proving themselves, and that in itself is a very difficult thing in the medical devices world, for sure.
Okay, so this is an aside.
Yeah.
That was such a good answer for a very poorly phrased question. That was awesome. That was awesome. You 1,000,000% picked up what I was putting down there, and when I was very worried that I had misread it.
No, I got you there.
That was awesome.
I got you there.
That was awesome. Okay. So, actually, what time are we at? 5:09?
At 5:09.
Okay, we got a couple more minutes.
Okay.
I got a couple more questions for you.
Awesome. We can speed run it too. I'm happy to do that. Favorite color?
So, ultimately, okay, here's another question that might brush up against your NDA. How close are you to actually using these to start diagnosing people?
Ooh. See, that's going to be a difficult one for me to answer. Right. I don't think I'm allowed to say, I saw the statistics, and I don't think I'll be able to talk about it. It's, let's put it this way. There's the Bill and Melinda Gates Foundation, the BMGF Foundation, huge into investing. They look at startups. They try to make it. They give money out a lot to startups to get kicked off. And so Noze got a BMGF grant. They were one of the Canadian companies that got one, and it's a low amount of Canadian companies that get them. So a small percentage to start up. Nice. They are the first ones ever to receive a second round investment.
Wow.
From the BMGF Foundation.
That's insane.
Ever in Canada.
That's insane.
So there's a lot of people who are so interested in this technology. And you should read the publication that they put out on their website about what they're doing. But essentially it's under the idea that the BMGF sees the vision. They see everything that Ashok and Kareem Ali, the CEO, have for the company, and they believe in them as a lot of people I think should, and so they want to take it as BMGF would. They want to take it to some underdeveloped countries, which it's great. It's a cost-effective diagnostic tool. That's huge. Cost-effective diagnostic tool in remote areas. Come on, that's what you want.
And small, so portable.
Super portable. Yeah, can take it wherever you go. So the whole idea was that they started a kind of the terms of it, if you will, was that they were going to investigate tuberculosis diagnosis in Kenya. So that was going to be kind of the foothold that they could get into the world. So when I talk about that, this technology has huge upsides and the potential for it is really great. It's not just a intern engineer that saw this. You could see the dedication in everybody that worked there was off the charts, but the belief that somebody outside the organization also has is just as big as the belief that was internal.
True.
So I think I don't think I obviously can't go into specifics, but there's a lot of support for the technology.
That's awesome. Yeah. That's awesome. So I want to ask now about the other part of your company, which is the AI model of the chip. Can you just give us a quick once-over of how does AI play into this? Is AI like reading the data?
Yeah, so it's super cool, and I'm going to be super honest with you. This will be a pretty high level because the few times I had it explained to me, and I will stress few, I got lost in the sauce. There was so much going on that I thought was so cool that it was very complex, and it's a very difficult thing. But essentially what they are doing is pushing the boundaries of what is currently known for medical AI. And what the AI model as a whole is really doing is not only is it gathering all this data to one thing to develop one AI model they're talking to each other. It's picking up from different chips. It's reading. So it is reading the data. So the data gets, there's the chip has a sensing array. The VOCs get on that sensing array. It picks up, turns that data into something useful, into some binary or whatever. And it reads all of that. But it's not just looking for, did sensing element 1, 4, and 6 light up?
Okay.
Because anything could do that. It's looking at, and VOCs are more complicated than that. The chip is more complicated than that. How quickly did that get absorbed? How long did it stay? How long did it take to go away? How did humidity play a role in the sample collection? What is all this? So what they had was all these different markers, and there's so many of them that they used to get this big sort of analysis of one sample.
Okay.
And then you're comparing that to what you already have. And what's it called? There's a name for the type of, it's like one left out. I butchered that name, but it's something similar, where when you're building these models, you take a look at the bigger picture about all the samples that you've collected, and you say, okay, based on all of these samples, I'm going to take one out, make a model based on everything there, and I'm going to throw that sample back in. Does it correctly predict what group it goes into?
Oh, okay.
So if you can do that, that's how you can sort of, knock on the door of your false positives, false negatives. Because really what you're looking for is, at the end of the day, you're looking for, do you have it or not?
Right.
And more often not, you care that you don't have it. So when you're talking about sensitivity and specificity, it's hard to, I mean, I'm in a stats class right now where all we're talking about, well, not all we're talking about, but what we were talking about was how can we buff up our sensitivity and specificity? And you want high levels of both. But at the end of the day, like, reality is reality. Sometimes you can't always get what you want. So how do you make the best version of it? So do you care? And that's going to be dependent for not only, it's going to be specific to each disease. Is it that you definitely have it, or you definitely don't have it? Because then that changes what metrics you go after, how you change, how you want that model to evolve, to all of that. And so the model itself, albeit way over my head, was actually pretty simple once you boil it down to read a sample, see the markers, compare the markers, where does it land? And not only where does it land on this group, but all those samples that we just collected from the other device, how does it fit in here? Because it can't just be one. Right. If it's just one, that's how they fail. That's how your company fails. That's how you make one really good thing that only one person can use, because it's tailored, and you don't want it to be tailored. You want it to be as least. I know in a lot of the stuff that we do through our program, we talk about like patient specific. Patient specific is like the way to go. We always want like tailored things. This is about as least tailored as you want. You want it to be like, given your breath sample, which is a tailored thing, let's compare to like a lot of things, because what we're looking at is metabolic processes. That's how those VSCs get into your bloodstream. Sometimes we don't know all the metabolic processes, all the intermediate steps, but we might know what comes out. So then we know what to look for. It's pretty cool.
That's super cool. So this AI is collecting tons of medical data, or theoretically will be collecting tons of medical data.
Yeah.
Right? That is I'm going to throw you a bit of a curveball here, if you may. How is that AI going to keep the data safe? Like, what is the sort of do you know about any of the regulatory basis of keeping healthcare data like that?
I don't know about like specifics about it for sure. I couldn't tell you, but all those things do fall under the same category of, like, if you give a blood sample, where does that data go? How is that data protected? It would follow the exact same under that. It's another sample. It's another thing to go. It's another method of testing that can go in a medical diagnostics toolbox, if you will, to pull out whenever you need. But you need to keep a nice lock on that toolbox for sure.
Of course.
But yeah, when you were saying like collecting tons of data, that is something that I kind of failed to mention about why this is so difficult. Because when I joined up, I was like, well, this seems easy. Or not easy, but this seems like, a no-brainer. Why haven't more people done it?
Sure.
Not only is it incredibly difficult given trying to make something that's universal to everybody. So that's where the AI model can fix that. Not only is it hard to control for some of the variables, like humidity, like, flow path and all of that. They have methods of doing that. But another really important one is, how do you train all this? How do you train your sensor? How do you tune your sensor? How do you do all that? Train it. You need data. You need big vats, crazy amounts of data. And if you look at something like, if you're looking at like blood samples, for instance, or I don't know, we could break it down even further. Look at large language models.
Okay.
They're trained on language. They're trained on speech. They're trained on text. They're trained to hear stuff, to analyze it, to see. They have a lot of data to work on. And that's why, Chat and like Claude and Truth, like all these ones are like pretty great. And that's why people that we know have even been able to implement like large language models, because there's so much data out there that they've been able to pretty fine tune them up until this point. You don't have that luxury with scent. Who's capturing scent data? Who's capturing scent data and labeling it? Because unlabeled data is kind of useless.
Totally useless.
So a big, push is also, can we manufacture our own data? And it turns out it's possible. Very difficult, but possible. And each of those samples that you get from a single patient becomes that much more valuable, because you don't know if you can use the next one or the next one after that or the next one after that. So you need to, everything becomes a lot more precious in that, because the AI model only gets better when you feed it data. Right. And we just simply, we're not like we were, I gave samples to just having collection. So it's being trained off my breath, but which is pretty cool. But, it's definitely a data scarcity issue. But that plagues everybody right now, which sort of levels the playing field. But it's whoever can break through that barrier, they got the door wide open. Now you just need to, now you have everything. It's like if you had all the photos in the world, or you had a majority of the photos. You could train a model to like AI generate art very well. But if you were the first one that had a camera, you were able to train that AI model that much quicker than everybody else who was like painting pictures and then sending it to it, something like that.
Fair enough. Okay, so we are at 5:20, so I think I really only have one more question to you.
Okay.
Which is going to be a data question again.
Cool.
So you just mentioned that you provided your own breath to help train this model, right?
Yeah.
Which is more important? Breath samples from the negative, breath samples from healthy people, or breath samples from sick people?
All of it.
Okay.
It's not one or the other, because anything gives you another clue. Anything gives you another marker. It gives you a little bit more information. Information is what's valuable. Obviously, the more sick people you can get, you can kind of figure out the correlation between them. But the flip side of it is, well, all these healthy people, we can figure out the correlation between them across broad populations, across all of this. And then when you compare it to a sick person, you should see something different. So information becomes the most valuable thing. I think it would be naive to say that one is necessarily much greater than the other, because it's all important. At the end of the day, obviously, if you have no sick people or one sick person and you only have their sample, that's not good. But if we're looking at like large scale, obviously you need X amount of sick people to be able to create a profile that represents a sick person, but you also need the healthy people to be able to compare to, or else you're never super gonna know.
Just leave your bookings.
We're getting kicked out.
We're getting kicked out.
Wow.
Luckily,
that was kind of a wrap.
That was kind of a wrap.
Sweet.
But, okay, wait. That's a wrap unless you have a quick answer to this question. Yeah. And you just tell me if you have a quick answer or not.
I can do it.
So, based on what you're telling me, where there's not as much a difference between a breath sample from a sick person versus a healthy person, why is this technology limited to only certain diseases right now? Couldn't this just be infinitely expanded to any disease?
That's yeah, that's the idea. The limiting factor becomes like, do we know what we're looking for?
Right.
And, the VOCs that are present come as byproducts of the metabolic pathways that are involved in whatever disease that you have. So studies need to be run. Biological plausibility needs to be done to say, okay, is what we're seeing really this disease, or could it be just a side effect of this? But honestly, with a lot of these AI models, and I know it's kind of thrown around all the time that say like anything is possible, but right now the horizon doesn't look that. The horizon is limited by the research. If you don't have research to support, you don't have a basis to go off for. If you start looking for a needle in a haystack in a bunch of sick people that somehow have the same disease, you're going to be picking for a while. Right. But if you have a study that says, hey, these are the byproducts that we found from all of these people's breast samples that had the same, underlying cause, you have a starting point, and you can go from there.
That is awesome. Josh, thank you so much for coming to talk to us today. I think that is going to wrap up our episode. As always, thank you so much for tuning in to this episode of the iCast. Josh, you have any closing remarks you want to say to the people?
No, thank you to the listeners, and shout out Griffin,
shout out to
the
Griffin.
News person.
He's the iScientist social media guru.
Thank you, Griffin, for making the thumbnail. We really appreciate it.
All right, everybody. Hope you have a great day, and you will be hearing from me later.